Hello everyone. In this section, we will discuss the DC circuit analysis of bipolar junction transistors, or BJTs. This is the introduction to Case 3. In the previous section, we finished Case 2 of BJT DC circuit analysis. Now we move on to Case 3 for an NPN BJT. In this circuit, the base, collector, and emitter terminals are each connected through a resistor. We first assume that the BJT operates in active mode, so VBE is approximately 0.7 volts, and beta is given. As before, we begin with the current path from the base to the emitter. Here we isolate the entire base to emitter current path. Starting from the DC bias voltage VBB, the path passes through RB, then through the BEPN junction, then through RE, and finally reaches the emitter side DC bias voltage, negative VEE. The total voltage difference along this path is VBB minus negative VEE. This total voltage is dropped across three elements, the resistor RB, the BE junction, and the resistor RE. Therefore, VBB minus negative VEE equals VRB plus VBE plus VRE. After rearranging the equation, the total voltage available across the two resistors is VBB plus VEE minus VBE. This equals IB times RB plus IE times RE. In active mode, IC equals beta times IB, so IE equals IB plus IC, which becomes 1 plus beta multiplied by IB. This current relationship is valid only when the transistor is operating in active mode. Substituting IE equals 1 plus beta times IB into the loop equation gives VBB plus VEE minus VBE equals IB times RB plus 1 plus beta times IB times RE. After factoring out IB, the total resistor voltage equals IB multiplied by the quantity RB plus 1 plus beta times RE. In other words, when viewed from the base side, the emitter resistor behaves like a larger equivalent resistance equal to 1 plus beta times RE. The equivalent circuit at the bottom shows this idea. The voltage drop across RE, which is originally IE times RE, can be described using the base current IB instead. Since IE equals 1 plus beta times IB, the same voltage drop becomes IB times 1 plus beta times RE. Therefore, we can reflect the emitter resistor to the base side by multiplying its resistance by 1 plus beta. This is called the resistance reflection rule, and it lets us solve for the base current more quickly. Using the reflected resistance, the base current IB is equal to VBB plus VEE minus VBE divided by the quantity RB plus 1 plus beta times RE. After IB is found, the base voltage VB can be calculated as VBB minus IB times RB. Once IB is known, the emitter current IE is 1 plus beta times IB. Then the emitter voltage VE can be found from negative VEE plus IE times RE. Equivalently, VE can also be obtained from VB minus VBE, which is approximately VB minus 0.7 volts. The collector current IC is IE minus IB, or directly beta times IB. Then VC equals VCC minus IC times RC. Finally, check whether VCE is greater than 0.3 volts. If it is, the active mode assumption is correct. If it is not, we must redo the analysis using the saturation mode assumption. In the analysis above, we use the total voltage drop across RB and RE in the base to emitter path. That voltage is VBB plus VEE minus VBE, and it equals IB times RB plus IE times RE. By replacing IE with 1 plus beta times IB, we reflected the emitter resistor to the base side as an equivalent series resistance. The same idea can also be applied in the opposite direction. Instead of expressing the loop current in terms of IB, we can write IB as IE divided by 1 plus beta. After factoring out IE, the total resistor voltage becomes IE multiplied by the quantity RB divided by 1 plus beta plus RE. This means the base resistor can be reflected to the emitter side by dividing RB by 1 plus beta. The equivalent circuit at the bottom shows this second version of the resistance reflection rule. The voltage drop across the base resistor, originally IB times RB, can be described using the emitter current IE. Since IB equals IE divided by 1 plus beta, the equivalent resistance becomes RB divided by 1 plus beta. So when RB is moved to the emitter side, its resistance must be divided by 1 plus beta to keep the same voltage drop. Using the reflected base resistance, IE can be found immediately. IE equals VBB plus VE minus VBE divided by the quantity RB divided by 1 plus beta plus RE. After IE is known, VE equals negative VE plus IE times RE. Then IB equals IE divided by 1 plus beta. V can be found either from VE plus VBE or from VBB minus IB times RB. Finally, IC equals IE minus IB or beta times IB, and VC equals VCC minus IC times RC. As usual, we check whether VCE is greater than 0.3 volts to confirm active mode operation. For case 3 BJT circuits in active mode, the resistance reflection rule is very useful. RB and RE can be treated as equivalent series resistances after applying the proper scaling factor. If RE is reflected to the base side, its resistance is multiplied by 1 plus beta. If RB is reflected to the emitter side, its resistance is divided by 1 plus beta. Now let us consider the same case 3 NPN circuit in saturation mode. In saturation, VBE is still approximately 0.7 volts, and VCE is approximately 0.2 volts. However, the resistance reflection rule can no longer be used because the fixed active mode current ratio between the three terminal currents no longer holds. We still begin with the base to emitter path, but now we choose the base voltage VB as the unknown variable. Starting with VB as the unknown, the base current is IB equals VBB minus VB divided by RB. Since VB is the only unknown, this expression contains only one unknown. Next, VE equals VB minus VBE, and VBE is approximately 0.7 volts. Therefore, the emitter current IE equals VE minus negative VEE divided by RE, or VB minus 0.7 volts plus VEE divided by RE. Again, the only unknown is VB. Under the saturation mode assumption, VCE is approximately 0.2 volts. Therefore, VC equals VE plus VCE. Since VE equals VB minus VBE, we can write VC as VB minus VBE plus VCE. The only unknown is still VB. After VC is written in terms of VB, the collector current can be calculated as VCC minus VC divided by RC. Substituting VC equals VB minus 0.7 volts plus 0.2 volts gives IC equals VCC minus VB plus 0.5 volts divided by RC. At this point, all three terminal voltages and currents are expressed in terms of the single unknown VB. To solve for VB, we use the three-terminal current relation IE equals IB plus IC. Once VB is obtained, all three terminal voltages and currents can be calculated directly. After finishing the NPN version of case 3, we now consider the same circuit structure using a PNP BJT. We again assume active mode operation, so VEB is approximately 0.7 volts and beta is given. The analysis also begins with the current path from the base to the emitter. Here, we isolate the base to emitter path for the PNP circuit. Starting from the base side DC bias voltage VBB, the path goes through RB, then through the EB-PN junction, then through RE, and finally reaches the emitter side DC bias voltage VEE. The total voltage difference along this path is VEE minus VBB. This voltage is dropped across RB, the EB junction, and RE. Therefore, VEE minus VBB equals VRB plus VEB plus VRE. After rearranging, the voltage available across the two resistors is VEE minus VBB minus VEB. This equals IB times RB plus IE times RE. Since IE equals IB plus IC, and in active mode IC equals beta times IB, we get IE equals 1 plus beta times IB. Again, this beta relationship is valid only in active mode. Substituting IE equals 1 plus beta times IB gives VEE minus VBB minus VEB equals IB times RB plus 1 plus beta times IB times RE. After factoring out IB, the total resistor voltage equals IB multiplied by the quantity RB plus 1 plus beta times RE. This is the same resistance reflection rule introduced in the NPN case. The reflected equivalent circuit is shown at the bottom. The emitter side resistor voltage, originally IE times RE, is rewritten using IB. Because IE equals 1 plus beta times IB, the equivalent resistance becomes 1 plus beta times RE. Therefore, when the emitter resistor is reflected to the base side, its resistance must be multiplied by 1 plus beta. Using this reflected resistance, the base current IB equals VEE minus VBB minus VEB, divided by the quantity RB plus 1 plus beta times RE. After IB is found, the base voltage VB equals VBB plus IB times RB. Next, IE equals 1 plus beta times IB. The emitter voltage can be calculated as VEE minus IE times RE, or directly as VB plus VEB. The collector current IC equals IE minus IB, or beta times IB. Then VC equals negative VCC plus IC times RC. Finally, we check whether VEC is greater than 0.3 volts. If it is, the active mode assumption is correct. Otherwise, the circuit must be reanalyzed in saturation mode. We can also use the other form of the resistance reflection rule by reflecting RB to the emitter side. In that case, IE equals VEE minus VBB minus VEB, divided by the quantity RB divided by 1 plus beta plus RE. After IE is obtained, V equals VEE minus IE times RE. Then IB equals IE divided by 1 plus beta. The base voltage VB can be found as VBB plus IB times RB, or directly as VE minus VEB. Finally, IC equals IE minus IB, or beta times IB, and VC equals negative VCC plus IC times RC. Now let us analyze the case 3 PNP circuit in saturation mode. In saturation, VEB is approximately 0.7 volts, and VEC is approximately 0.2 volts. However, the resistance reflection rule cannot be used because the fixed active mode current ratio no longer applies. We again start from the base to emitter path and choose the base voltage VB as the unknown variable. Starting with VB as the unknown, the base current is IB equals VB minus VBB divided by RB. Since VB is the only unknown, this expression contains only one unknown. Next, VE equals VB plus VEB, and VEB is approximately 0.7 volts. Therefore, IE equals VEE minus VE divided by RE, or VEE minus VB minus 0.7 volts divided by RE. Under the saturation mode assumption, VEC is approximately 0.2 volts. Therefore, VC equals VE minus VEC, which is the same as VB plus VEB minus VEC. The only unknown is still VB. After VC is written in terms of VB, the collector current is VC minus negative VCC divided by RC. Substituting VC equals VB plus VEB minus VEC gives IC equals VB plus 0.5 volts plus VCC divided by RC. Therefore, all terminal voltages and currents are now expressed using the single unknown VB. Finally, we use the terminal current relation IE equals IB plus IC to solve for VB. After VB is found, all terminal voltages and currents can be calculated. Now let us work through a case 3 NPN example. We first assume active mode. Therefore, VBE is approximately 0.7 volts and beta is 100. As usual, we begin with the base to emitter path. Using the resistance reflection rule, we solve for IB. The total resistor voltage is 8 volts minus negative 5 volts minus 0.7 volts. The emitter resistor is reflected to the base side, so the denominator is 100 kiloohms plus 100 times 1 kiloohm. This gives IB approximately 0.0612 milliamps. After IB is found, VB equals 8 volts minus 0.0612 milliamps times 100 kiloohms, which gives 1.88 volts. Then VE equals VB minus VBE, so VE equals 1.88 volts minus 0.7 volts, or 1.18 volts. IE equals 1 plus beta times IB, so IE is about 6.18 milliamps. Then IC equals IE minus IB, which is about 6.12 milliamps. From this, VC equals 10 volts minus IC times RC, giving 3.88 volts. Finally, VCE equals VC minus VE, which is 2.7 volts. Since this is greater than 0.3 volts, the active mode assumption is correct. Next, let us look at a case 3 example using a PNP BJT. Again, we use the resistance reflection rule to solve for IB. The total resistor voltage is 10 volts minus 8 volts minus 0.7 volts. The denominator is 100 kiloohms plus 1 plus 100 times 1 kiloohm. This gives IB approximately 0.00647 milliamps. After IB is found, VB equals 8 volts plus 0.00647 milliamps times 100 kiloohms, giving 8.647 volts. Then VE equals VB plus VEB, so VE equals 9.347 volts. IE equals 1 plus beta times IB, giving about 0.65347 milliamps. Then IC equals IE minus IB, which is about 0.647 milliamps. VC equals negative VCC plus IC times RC, giving negative 4.353 volts. Finally, VEC equals VE minus VC, which is 13.7 volts. Since this is greater than 0.3 volts, the active mode assumption is correct. Now let's consider another case 3 PNP example under a different set of circuit conditions. Using the resistance reflection rule again, the total resistor voltage is 5 volts minus 0 volts minus 0.7 volts. The denominator is 10 kiloohms plus 1 plus 100 times 1 kiloohm. This gives IB approximately 0.0387 milliamps. After IB is found, VB equals VBB plus IB times RB, which is 0 volts plus 0.0387 milliamps times 10 kiloohms, or 0.387 volts. Then VE equals VB plus VEB, giving 1.087 volts. IE equals 1 plus beta times IB, giving about 3.91 milliamps. IC equals IE minus IB, which is about 3.87 milliamps. Then VC equals negative VCC plus IC times RC, which gives 33.7 volts. Finally, VEC equals VE minus VC, or about negative 32.6 volts. Since this is less than 0.3 volts, the active mode assumption is wrong. We must reanalyze the transistor in saturation mode. When the PNP BJT operates in saturation mode, VEB is approximately 0.7 volts and VEC is approximately 0.2 volts. Since all three terminals are connected through resistors, we choose the base voltage VB as the unknown variable. Starting with VB, the base current is IB equals VB minus VBB divided by RB. In this example, that is VB divided by 10 kiloohms. Then VE equals VB plus VEB, so VE is VB plus 0.7 volts. The emitter current is VEE minus VE divided by RE, or 5 volts minus VB minus 0.7 volts divided by 1 kiloohm. Using the saturation condition, VEC approximately equals 0.2 volts. The collector voltage is VC equals VE minus VEC. Therefore, VC equals VB plus 0.7 volts minus 0.2 volts, which simplifies to VB plus 0.5 volts. After VC is written in terms of VB, the collector current is VC minus negative VCC divided by RC. Substituting VC equals VB plus 0.5 volts gives IC equals VB plus 5.5 volts divided by 10 kiloohms. The only unknown in all these expressions is still VB. Finally, we use IE equals IB plus IC to solve for VB. This gives VB equal to 3.125 volts. Then IB is 0.3125 milliamps, VE equals 3.825 volts, IE equals 1.175 milliamps, VC equals 3.625 volts, and IC equals 0.8625 milliamps. The forced beta is IC divided by IB, which equals 2.76 amps per amp. This concludes the introduction to Case 3 of BJTDC circuit analysis. Please look forward to the next lecture. See you next time. Bye.